In Chapter 9, we will look at hypothesis testing based on a single sample. So this starts on page 425 of your textbook. This video will just be a basic introduction. We'll do a few examples, and you should get the basic idea about what hypothesis testing is. Now, hypothesis testing sounds like a really terrible big thing, but actually it just means we're testing a theory that we have. So hypothesis is just a fancy word for theories. Now, in your study guide, you will get a description of exactly what you need to do in this unit. So you'll see which pages of your textbook you need to read. Please read those carefully so that you don't miss any critical information. And then you must be able to name the elements of a test procedure. You must be able to define and formulate both your null and alternative hypotheses for a specific problem. Define type 1 and 2 errors. We'll deal with this in the next video, as well as understanding the relation between risks, alpha and beta. And all of this terminology you need to understand as well, and be able to apply it in practice. Now, let's start with a research problem. So like I already said, a hypothesis test is actually just a test about a theory that we have, so nothing major. And let's say that we are interested in testing a theory about the average weight of males, so 19-year-old males, and we want to see if this has increased since 2010 when it was 70 kilos. So when we're doing hypothesis testing, we have a research problem, and that implies that we have two complementary events. So the first is stated as a claim or an assertion, and in this case it is that the average weight has stayed the same. So we will just assume no change, same thing as before. And then we get the other claim, which is actually the one that we're interested in. So we might be interested in knowing whether the average weight has increased, and for that, to make that, or to say that that claim is correct, we need proof. And that is what we will get from sample data. So we will collect a sample, and in this case, because we are working with the mean, so it's again very important that you understand what your question is about. So here we're talking about average weight, and that means that we will want to calculate the mean weight. So if we were dealing with something like a proportion or a variance, obviously we would calculate the proportion or the variance in that situation. Now, once we have our sample data, we can use that and compare it to this historical information that we have, the theory that we are trying to disprove, and then we want to see if we have sufficient evidence to support this hypothesis or this theory that we have. And the theory that we want to support is the one here, the thing that we're interested in. Now, how do we do this? In statistical notation, we start by constructing our null and alternative hypothesis. So this H with the 0 at the subscript, that is our null hypothesis, which you can see relates to this first claim that we have. So the thing that we're assuming is true until we get evidence to the contrary. Then the next hypothesis is called the alternative hypothesis, and that is that the mean weight has increased. Now I want you to notice here, I've just written 70. I didn't write the units, so I didn't write 70 kilos. We never write units when we write our hypotheses. When we get to our conclusion when we say what we've found out, then we will include units again. But when we're doing our calculations, we don't write the units. Now, our alternative hypothesis can also be written in different textbooks. They write it differently. So some will write it with a capital A, some will write it with a 1 instead of an A. That is perfectly acceptable as well. So your textbook is doing it with the lowercase a. You sometimes might see me writing the uppercase a. I haven't used the other notation in years, so I probably won't use it. But just be aware, when you see it somewhere else, it is not something strange happening. Same thing, different notation. Now, the next thing is we would need our sample. So let's say in this case that we are going to get a sample of 100 19-year-olds and weigh them. And from those 100 19-year-old males, we get an average weight of 72 kilos. Now we might wonder, is this really a bigger weight? But we'll get to that just now. Then we are going to compare to our historical mean, and our historical mean is 70. And you'll notice that I've written it with a mu naught here. That is called the hypothesized mean. We will talk more about that later as well. But that is the symbol that we use for this value that we have in our hypothesis test. And then we just need to go and make a decision and decide, is that 72 high enough to tell us that our mean has increased, or is it still a value we expect to see? So we are going to use the sampling distribution, which we covered in a previous chapter, to think about how this x bar value varies naturally, so that we can decide, is the 72 a value that still comes from a distribution with a mean of 70, or does it seem to tell us that the distribution has changed? So if we look at this problem, we are dealing with x bar, because remember, x bar is used to estimate mu. So if we want to estimate mu, we can say here mu hat is being estimated by x bar. So sorry about that line, sometimes happens. But basically that is our estimator. Our calculated value of x bar is our estimate. So 72 is our estimate. X bar, capital letters, that is our estimator. So that's the function we use to estimate. So everything from the previous chapters still with us. Now, if we look at our null and alternative, we want to see if the mean has increased. So we'll get back to that. But there's a little bit of extra information here that's really important, and that is our sample size. So we said here we're dealing with a sample of 100. Now I've drawn a sketch here of the normal distribution, and I'm hoping you already wondered why I did that. Because if we look at our problem, nowhere on the previous slide did I say that the average weight of 19-year-olds is normally distributed. So we go back to the central limit theorem, and the central limit theorem tells us if my sample is large enough, my sample of x values, then x bar, which is based on those x values, will be approximately normally distributed. So that is why I can draw this normal curve. Now, if our average weight has stayed the same, then these x bar values should be distributed symmetrically around 70. So that is what we have here. So we expect our x bar values to be close to 70 if the population mean, or the average weight of the males currently, is still 70. So if that is the case, then we can go back again to our central not the central limit theorem, the empirical rule. So let's think of the empirical rule. I just want to get a different color pen if it allows me to. Technology does not always work with us. There we go. So let's make this red for now. Now, the empirical rule that you did last semester tells you that within one standard deviation of the mean, so the mean plus one standard deviation and the mean minus one standard deviation, we don't know what sigma is in this case, but we're not going to worry about that right now. We expect roughly 68% of our observations. So if this population is still centered around 70, then a lot of our values for x bar should be close to 70 as well. Now, if we find an x bar value which is much larger than 70, then it could be, we can ask ourselves, is this by chance, or is it actually normal? So let's think about the 72. Let's say the 72 lies over there. So that is where we find 72. So if we consider what the chances are of getting a value of 72 or larger, you can see here this area under the curve quite small. So what the chances of that happening by chance is actually quite unlikely. So that 72, let's say, lies over here, then it's highly unlikely that mu is still 70. So that's the idea behind the hypothesis test. So this means that this is an indication that mu is probably larger than 70 because we expect that most of our x bar values will lie close to 70 if 70 is still the population mean. So that is the concept that we're working towards. Now, that just means that the probability that x bar is larger than that observed x bar value, if that is very small, then we are going to reject the null hypothesis. So we're saying here that if our x bar value is far away from the hypothesized value of 70, then it's unlikely that the distribution has remained the same. That mean has probably shifted upwards. Now, we'll go through the whole testing procedure in at a later stage. So I just want you to get the concept first. So we said now average weight has stayed the same or not increased. That is what our null is. So we are going to always write our null hypothesis with an equal sign. So when we do this test, we're actually testing the alternative, which means we are just testing to see if it's more than 70. It might actually be that the mean has decreased, but we're not testing for that. We're only testing for this thing that we have in the alternative. Now, that's what we're looking for, the proof we're looking for. So we can equate this to a court of law analogy. So you are innocent until proven guilty. So you can see the innocent as your null, and your alternative is that you are proven guilty. And yet again, my pen is misbehaving. We will just ignore that. Now, let's get to the definition. The definition of the null hypothesis, we denote it, as I already said, by H0, and it is the claim that is initially assumed to be true, so a prior belief claim. That's another way of saying it. The alternative hypothesis, denoted by HA, and like I said, you can do a capital A, you can do a 1 there, doesn't matter. We're just going to stick with the lowercase a because your textbook does it, is the assertion that is contradictory to H0, and it's the thing that we are interested in. So we will reject our null hypothesis in favor of the alternative if our sample evidence suggests that the null is false. And if the sample doesn't contradict the null, then we just carry on believing what we are believing currently. So unless you can prove otherwise, you stick with the null. So two possible conclusions is therefore reject the null, or fail to reject the null, or do not reject the null. Doesn't matter how we phrase it in that sense, but never, ever, ever accept the alternative. And we will get back to that later. Now, what we are going to test in this module is we are going to test claims, firstly now in this chapter, for a single population parameter. So that's something like the population mean, the population proportion, or the population variance. And you can, of course, test for other parameters as well. We'll stick to these three. Then in the next chapter, we will do hypothesis tests where we look at two population parameters. So we could look at a difference of means, difference of proportions, or one variance relative to another one. So examples of this would be if you wanted to compare the average mark in the last test for the males compared to the average mark for the females. So then population 1 is maybe the males, population 2 is the females, and you want to see if there's a difference there. Or the proportion that passed for the students who came to class, watched their videos, all of that, versus the ones that didn't do all of that. Then in the next chapter, we expand on that and we say, now we don't want to just compare two means, we want to compare more than two means. So that will be in chapter 11. Chapter 13 will then look at relationships between variables, so we'll do some tests there. And then, in chapter 12, and then in chapter 13, we will look at the shape of the distribution. So we can do hypothesis tests to see if a population is normally distributed, or binomially distributed, or chi-square distributed, or pretty much any distribution we're interested in. So I think we will focus on normal, binomial, the ones that you are familiar with. So that will be in chapter 13. So you can see that it's really important to understand the basics of hypothesis testing, and it actually is quite good news for you guys, because if you understand the basics, then all of these are just small differences in your testing procedures that you need to be aware of, but it's pretty much doing the same thing over and over. So you just need to be able to identify what you're testing, which test to employ, and then the rest is easy peasy. So let's move on to our court of law analogy again. So we have a hypothesis test and a trial. So if you're like me, you would love Law and Order and those types of shows, so you will understand this quite easily. But either way, you should understand it. So let's say in a trial, a criminal trial, we have a defendant that's placed on trial on a charge, and we assume that this person is innocent until the evidence points us in the other direction. So with the hypothesis test, the same thing happens. So I've just included here an example with the mean. Of course, it can be proportion, it can be variance, it can be any number of things. So we will go and test that, and our null will always be with an equal sign. Alternative is always going to be, you test whether it's gotten smaller, bigger, or if it's different. And we assume the null is true until we can prove otherwise. Now, the next thing is, in a trial, proof of guilt must be beyond a reasonable doubt, and the same thing applies in a hypothesis test. And there we will talk about these risks. So we'll talk about alpha, the significant level which is chosen, common choices for that. We'll get to all of this later on as well. And then you'll see there's actually a second risk that we need to consider, which is beta. But that, again, later on. That is our choice, which provides our threshold for what reasonable doubt is. Then we need to decide on a type of trial, whether it's by judge, jury, in South Africa, which court it goes to, those kinds of things. And the same kind of thing happens here. So we need to decide on what type of test, and that is, of course, determined by what we are testing. Are we doing a test for the mean, for the proportion, for the variance, and there's a few factors that we need to keep in mind, what assumptions need to be met for each of these tests. Then we would collect evidence, and we collect that from a sample. So I want you to recognize here already that when we do hypothesis testing, we come up with our theory that we want to test first, and then only do we look at what the sample tells us. So the sample never tells us what we will be testing. Then evidence is presented and debated or considered, whatever you want to call it. And in a hypothesis test, that happens by calculating what we call a test statistic and a p-value. P-values will only be dealt with in section 9.4. So that is towards the end of this chapter. And we need to do that in accordance to the type of test that we chose in that step 3 above. Now, in a trial, if there's reasonable doubt of innocence, so we doubt that the person is innocent and there's enough doubt, then the person is found guilty. And if there's not reasonable doubt or enough reasonable doubt, then we find them not guilty. Notice we did not say innocent. So in a hypothesis test, we will check whether our test statistic falls in a predefined rejection region. We will get to that as well. We can also do it with p-values. And if it falls in, our test statistic falls in the rejection region, then we will reject the null hypothesis. So we reject that thing that we assume to be true. And if it doesn't fall in that rejection region, then we don't reject the null hypothesis. So if we don't have enough evidence against the null, then we're not going to reject it. And then lastly, in a trial, you sentence or you free the defendant. And in a hypothesis test, it means that we are going to interpret the decision that we made in that previous step and decide what our conclusion is. So that is pretty much how a hypothesis test will work. So we're going to start with the basics, formulating our null and alternative. And there's a few rules that we need to keep in mind. So first rule it is always in terms of our population parameters. We don't do a hypothesis test to test what's happening in the sample. We're doing it to test what's happening in the population. So the null must always contain an equal sign. You can sometimes do it as well with a less or equal, greater or equal. In this module, we're just going to stick with the equal. I think when you get to second year, you will do it maybe with a less or equal or a greater or equal, but you will never be wrong if you just put an equal sign in your null hypothesis. Then your alternative, on the other hand, must never, ever, ever contain an equal sign of any form. So no equal, no less or equal, no greater or equal. It must never be there. So let's look at a few examples. So first example is we want to look at the shelf life of dried fruit. We want to see if it has been increased using a new additive. So the current additive is known to last 200 days. So in this case, first thing we're interested in, this is for an average. So when we're looking at the shelf life, it's not the proportion that's going to last more than 200 days. We're just looking in general here at a average. So that means our population parameter, remember it has to be in terms of a population parameter, is going to be mu, and the average that we currently have is 200. And you can see I have my equal sign in the null. Now, the alternative is always going to be the thing that we are interested in. So we want to see if shelf life has increased with this new additive, which means that we're going to test if the mean is now greater than 200. Now, the next example, we might want to know, are refrigerators still the same quality as in 2010? Proportion to be replaced under warranty in 2010 was 0.1. So you can see here immediately, we're not working with the mean, we're looking at the proportion. We're interested in what proportion will be replaced under warranty. So again, our null, nice and easy. We are dealing with proportion. Notice it's not p hat, it's p because it's the population parameter. And we want to assume that it's still 10% that needs to be replaced. We don't write it as a percentage. We always write it as 0 point something when we do a hypothesis test, never as a percentage, because a percentage includes units. So the alternative, we want to see, are they still the same quality? So if we're asking if they're the same quality or if it's changed, it means that it could be that less are being replaced by, under warranty, or that more are being replaced. So this one is actually asking us, is the proportion different from what it was before? And that's why we're putting a not equal to. And you can see no equal in the alternative, it's a not equal. Then our third example, a manufacturer claims a variation in battery lifetime seems to be reduced in their new release. So they've done an upgrade on their batteries and they think there's less variation in the battery lifetimes. So lifetime before the new release is known to have a variance of 10 hours squared. So here we're working with variance. So our null is going to be that the variance, and again notice population variance, is still 10. We assume it's the same unless we've proven otherwise. So the thing we're interested in proving is whether this lifetime has been reduced, or the variance in the lifetime has been reduced. So in other words, is the alternative, sorry, that has to be an A, is the alternative, or the alternative is that the variance is now less than 10 hours squared. Now, we have special names for all of these different tests. So the first one, if we look at the alternative, that's where we're going to get the name. So the alternative says greater, which means this is a right-sided test, because if you're looking at a number line, let's just draw a number line there. If we had 200 over there, then we think it has increased, so it's to the right side. So it's a right-sided test or an upper tail test. Then if we're looking at the next one, it is not equal to, so it's a two-sided or a two-tailed test. And the last one, because the alternative says less than, it means that we are dealing with a left-sided test or a lower tail test. So we'll use these terms interchangeably, but always our alternative is always going to tell us what side test we are dealing with, and a lot of how we do our test is determined by that fact. So you need to understand what we mean by right-sided, two-sided, and left-sided tests. So as an example, I want you guys to look at question 1 in your textbook. So we're going to work through this in a moment. I'm just going to suggest that you pause the video now for a moment and do this on your own, and then you can check your answers with me. Okay, so I assume that you have now unpaused the video and that you've completed this. So I've written the 3 rules that we need to abide by that we've learned so far. Remember, always in terms of our population parameters, we haven't indicated here whether it's the null or alternative. So this could be either. So let's decide for each of them as well whether it's an appropriate null or an appropriate alternative. And then null must always contain an equal, alternative must never contain an equal. So if we look at this, the first one, we do have our population parameter. And in this case, we have a greater than, which means this can't be the null. This can maybe be an alternative hypothesis. So this does comply with everything we need to make it an alternative. So we're all good. The next one, however, we are looking at the sample median. And that means that this is not an acceptable hypothesis. It can't be the null, it can't be the alternative, because it's not dealing with a population parameter. This next one is, again, this is the sample standard deviation. So because it's a sample standard deviation, it's not an appropriate hypothesis. So you cannot do that. Option D, we have sigma 1 divided by sigma 2. So those are both population parameters. So rule 1 is satisfied. We have a less than and a value, which means because it's a less than, this cannot be a null. So this can be an alternative. So that is fine. So also meets our criteria. Then option E is the difference between X bar and Y bar. And again, notice X bar and Y bar are both sample statistics. They're not population parameters. So again, not going to be a valid hypothesis. And then the last one, where we said lambda is less or equal to 0.01, where lambda is the parameter of an exponential distribution used to model component lifetime. So this is an example of a test that you could get in chapter 13, where we test parameters. And again, notice it's a population parameter. It's not a sample statistic. So rule 1 is obeyed. And if we look at this, because there's an equal, this cannot be an alternative. It can only be a null. So that would work. But again, like we said in our textbook, we are going to just always work with just an equal sign in the null. So to wrap up the definition of the null and the alternative, we have the null hypothesis, which is also called often the hypothesis of no change, or the status quo, or the favored hypothesis, or prior belief. There's no the hypothesis of no value, effect, or consequence, the hypothesis of no difference, of no improvement, and like we said, there's always an equality. So we can call it any of these things, or we can just call it the null hypothesis. Whereas the alternative hypothesis is indicating to us that there's been a change. So this is the thing that we need to prove, that we're interested in, and it can never include an equality. So the alternative, like we said, can only be left-sided, right-sided, or two-sided. So in your textbook, this is summarized as follows. So we have our parameter here. You can see it's very generic. We just use the theta, and that theta can, of course, represent something like mu. It can represent proportion, it can represent sigma squared, the variance, it can represent sigma. Pretty much any parameter that you can think of can be plugged in where we have that theta, and then we have a hypothesized value for that. And our alternative will be that the parameter has increased from that value, decreased from it, or changed. So it's not the same. So there we care about both direction. So in this case, again, implicit null hypothesis is less or equal, but in our textbook or in our module, we are going to stick with just always writing an equal. But it could actually be less as well. We're not testing the null though, we're only testing the alternative. So that's the only thing we're interested in. So if it's the equal or the same, makes no difference to us. We are interested in seeing whether it's increased, decreased, or become different. Now, if we look at question 2, I again want you to work through these on your own. Pause the video and give yourself a moment to just first check whether you are on the right track. And if you can do all these questions without me giving you the answers first, you know that we can't throw anything at you that you won't be able to handle. So pause the video now and I'll give you a moment to work through these yourselves. Okay, so I assume you have done that. So let's check each of these. So we have our 3 rules so far. The null, always in terms of a population, or both hypotheses in terms of population parameters. Null must always have an equal, alternative must never have an equal. So if we look at the first one, we have our population parameters. We have an equal in the null, a greater than in the alternative. Everything is fine. That one works. Now, the second one, we have our population parameters. So rule 1 is fine. We have an equal in the null, but over here we have a problem. There's also an equal in the alternative. So this is not valid. The next one, we have our population parameter. We, however, don't have an equal in the null, so that's a problem. And we have the equal in the alternative, so that's also a problem. So again, not valid hypotheses. If we had swapped the signs around, then it would have been fine. The next one is a difference of population means. So again, population parameters are here. That's fine in both hypotheses. We have the equal. We have something which is not an equal in the alternative, but notice here that we have a problem. These 2 values do not match, and they always have to match. So let's add a rule. Our next rule is that the hypothesized value must be the same in both of these hypotheses. So again, this is not the case, so it won't work. Now our next one, even though we have the equal sign and the not equal in the alternative, this is not valid because of the S squared. So this is our sample variances. So not valid hypotheses. In F, we have our population parameter. That's fine. We have the equal here. This is not fine. We have an equal twice. And we also have values that don't match. So this is definitely not valid. Then in G, we have our population parameters. And you'll see when we do tests for variance, we can do ratio tests as well, where we take the ratio of the 2 values. For the means, we tend to subtract them. Standard deviations or variances, we might do it differently, or we might do it with a ratio. So this is actually perfectly fine. And we have an equal in the null, which is good. We don't have an equal in the alternative, which is good. Our values match. Everything is fine. This is a valid set of hypotheses. And then the last one is that we have our parameters again. So these are 2 population proportions. So that's perfectly fine. Same thing there. We have an equal in the null. We have a less than there, which doesn't include an equal. So that's fine. These values match. Everything is fine. That is a valid test as well. So it's really important that you can define these correctly, otherwise you are going to run into big problems later on. Now, our next steps will be to determine our test statistic, or find our test statistic, decide on one, and decide on a decision rule. So to determine we find the sample statistic first, and we need to know that distribution of the sample statistic in order to do the test, and then we will compare that to a value assumed under the null hypothesis. So you'll see this term quite often, under the null hypothesis. It basically just means that we assume the null hypothesis is true. So we'll look at some test procedures, and a test procedure is basically just a rule based on our sample data that lets us decide whether to reject the null hypothesis. So if we think back to that first example we had, we saw that 72 is larger than the 70, but is it large enough? So that test procedure will tell us whether the value is large enough for us to reject the null hypothesis. So this test procedure is specified by the following. This is defined in your textbook. We have a test statistic, which is a function of the sample data, and you'll see that we have a few different test statistics that we can calculate depending on what situation we're in. And we'll start with a really basic one in this chapter, which we generally won't use too much. We will focus more on the ones given in section 9.2, but you'll get a basic introduction into a test statistic just now. Then a rejection region, which is the set of all the test statistic values for which we will reject the null hypothesis, and we will reject the null hypothesis only if our test statistic falls in the rejection region. So a lot of terminology to get used to, but you'll get the hang of it really quickly. Now, let's look at two examples. The first one, we say that suppose that 10% of computer circuit boards produced by the manufacturer is found to be defective. This is an example in your textbook. It's not labeled as an example. It's in the text of your textbook in between examples. But it should explain things quite clearly to you. So we have X, which is the number of defective circuit boards manufactured, or we can look at it from the point of view of a proportion, which is typically what we would do. But for now, let's work from the point of view of X. So we have an engineer that's claimed that he has improved the process, and you now will have fewer defective circuit boards produced, and we want to go and test that. So currently, our null is what we currently believe to be true, and until this engineer proves this to us, we will continue believing that we have 10% defective circuit boards. Otherwise, if he can disprove us, then we are proving the alternative, so that the proportion has decreased, the proportion of defective circuit boards. So we'll always state our null and alternative with this type of question in terms of proportions. We never state it in terms of X. Proportion is also much easier to understand than the number of defective circuit boards, because if you are looking at the number of defective ones, then you of course need to know what the context is. So how many are you looking at in total to say what the number is? So it's just better if we work from proportion, because everyone knows what 10% means. Now let's assume that we have a sample of size 200. Then under the null hypothesis, and again, under the null hypothesis just means that we are assuming that the null hypothesis is true. And if we assume the null hypothesis is true, that the proportion of defective circuit boards is 10%, then X will just have a binomial distribution. Remember, our sample size is 200, and the proportion of defective ones is 0.1. And from this, we can go and calculate then, in terms of the value of X, we can say, well, the expected value of X, if X is binomial, the expected value of X is just going to be 20. So it's 0.1 times 200. And we can also go calculate the variance if we wanted to know that. So that's just going to be under the null hypothesis. So we're using this value of P0. So remember, these values written here, shorthand way of writing it is P0. But whenever we give our hypothesis, we want to actually put the actual hypothesized proportion in here. P0 is just a placeholder until we know what those values will be. Now, if we really wanted to, and we will do this in future, we could also approach this problem to answer this question from the proportion point of view. So we know that p hat, which is just the number of defective items divided by my sample size, is approximately normal under certain circumstances, and this is the mean and the variance of p hat. So we will get back to that in a later chapter. So for now, we're just going to stick with working with x. And we might say, okay, so we know that if the null hypothesis is true, that we expect roughly 20 of the 200 circuit boards to be defective. So if we get a value of x of 20, or a value of x which is larger than 20, this is not contradicting the null, because remember, implicitly the null is actually that it is greater or equal to 0.1. That's not what we're interested in. We're interested in less than. So contradicting the null, even though it says equal, it's actually implied greater or equal in this case. Now, if we got a value of x, so we took a sample of size 200 and we saw much less than 20 circuit boards defective, then that does contradict the null hypothesis that 10% is defective. Because remember, we're proving this alternative. So if we get a value of x much less than 20, then it does contradict the null. It supports the alternative. Now, that means that we need a cutoff point. So we need to decide how much smaller than 20 must this value of x be for us to say that, okay, the null has been contradicted. So should it be 15? Should it be 14? Do we just pick a number out of thin blue air? How do we decide on this? So that is where our test statistic and our rejection region is required. So our test statistic is the thing that we're going to calculate. In this example, my test statistic is the value of x. It's testing what I'm interested in. And my rejection region is this cutoff point. Like, where do we decide that this is now small enough in this case? And that is my test procedure that's necessary. Now, a second example, cigarette manufacturer claims that the average nicotine content of a certain brand of cigarettes is at most 1.5 milligrams. So X is the nicotine content of the cigarettes. And the claim is at most 1.5. So if we write this in terms of hypotheses, then we're going to say the claim is that the average is 1.5. And then the alternative is that it is more than 1.5. So the at most is actually implied implicitly here in the null. And we want to prove this cigarette manufacturer wrong. So we're interested in contradicting them. So let's say we're doing this test from the consumer point of view. Then we are testing whether the average is more than 1.5. We want to disprove them. If you're the manufacturer, maybe you would want to prove that it is less than 1.5. So you need to read in the context of the question, who is doing the test? What are they interested in proving? So we're doing this one from the point of view of a consumer. So let's say our sample statistic that we're interested in using here is going to be X bar. Then, so we're going to look at the average nicotine content. Then we need to decide on a rejection region. So again, if X bar is roughly 1.5 or X bar is less than that, it doesn't do anything to prove our alternative. So in other words, it does not contradict the null. Although if we get an X bar value which is larger than 1.5, it supports this alternative. And then in other words, it does contradict the null. So that is what we are looking for. So we need to find a cutoff point, which is obviously then larger than 1.5, the value we're interested in. And again, we need to know, how do we choose this value? So we need to think about what our test statistic is and what rejection region is required. So in short, or in summary, our hypothesis testing procedure will be that we want to formulate our hypotheses, our null and our alternative. We want to then choose a test statistic and find a rejection region which is appropriate, and that you will see will be based on the test statistic that we choose. And then we want to collect sample data and calculate that test statistic. We'll then make a decision and come to a conclusion.